questions here. We're leading towards the topic about balancing. So we're looking at balancing our nuclear equations. And I'll talk about what that means in a second. But what we're looking at today is just getting the information that we've already got in our brains to try and link that to nuclear equations. So what's the term nuclear stability mean? When we talk about nuclear stability, what am I talking about? What do you reckon, Nick?
How stable the nucleus of an atom is.
Okay, I like that, the word nucleus. I like the word nucleus. Stable, what do you mean by stable? Because the word stability is in that. Connor. Connor, and then Acacia.
Well, it means that the atom is stable and it's not emitting any radioactivity.
Okay, it's not emitting radioactivity, it's stable. Again, we're using that word stable. What's that mean? Acacia, what do you think?
When it does not decay spontaneously.
Yep. Jason, you got a different answer?
When the nuclear falls within an atom, it's strong enough to keep the nucleus from coming apart.
Okay. Why does the nucleus come apart? What are the forces at play inside our nucleus? Jason?
Protons repelling each other.
Yep, which is called the? Starts with E? Electromagnetic force. So that's pulling them apart. If that was the only force, our atoms would be separated, wouldn't they? But there's another force, isn't there? Yep, the nuclear force, which keeps our atom together. It's like the glue that holds our atom together. So when we talk about nuclear stability, what we're saying is it's a balance between the force pulling it in, our nuclear force, and the force pulling it apart. Happy with that? And every atom's got a different amount of things that it wants inside it to be happy. So I'm going to put the solution to that is when our nucleus has equal EM and nuclear force. In brackets, it's happy. When our nucleus is happy, it's stable. Neither force is winning. So what is meant by the term isotope? What do you reckon, Aaron?
I reckon that it is an atom that has a different amount of neutrons but has the same amount of protons as its number in the periodic table, or its element.
Very good. So Aaron said it's got a different number of neutrons from the value in the periodic table. What do you think that value represents? The average? What do you reckon our expected value would be for our neutrons? Do you think that's a stable or an unstable atom? It's like carbon 12. See, it's the number we expect is 12, correct?
Yeah.
Does that sound like a stable or an unstable amount of neutrons?
Well, 12 neutrons make it unstable, basically.
Sorry, not 12 neutrons, 12 things in the nucleus. The number we see in our periodic table represents an approximation of the stable atom, correct? So what we're really saying when we've got isotopes is there is an unstable number of neutrons in the atom. I'll say that again. There is an unstable number of neutrons in the atom. And that's what the Springfield baseball team is called the? What's Homer do? Works in the power plant. So the word isotope and nuclear equations and nuclear physics are very heavily linked because an isotope means that we've got an unstable amount of things in our nucleus. Cool? So to deal with that instability, what does the atom do? How does it deal with that instability?
Let's go of the particles that doesn't need.
Let's go of particles in what part of the atom? The electron shell or the nucleus? Nucleus. Different types of decay. Can someone give me a type of decay that could occur? Will. Alpha. And what's alpha's mass? What's the mass of an alpha decay? What is an alpha particle? It's a helium atom which has got 4 mass and charge? +2. We've also got beta decay, beta plus decay, neutron decay, and gamma decay. Which one of those is different from the rest? Gamma. Why is gamma different? No mass, no charge. It's an electromagnetic wave. The rest are particles. So who would like to venture a guess as to what's going on with the rest of these? Let's start with neutron decay because we're all pretty familiar with our neutrons. What's the mass of a neutron? 1. What's the charge?
0.
Okay, beta decay. What's another? Do we know what we call beta decay? What is beta decay? It is an it's an electron. What's the mass of an electron? 0. What's the charge? -1. We've also got this special type of electron called a positron, and you'll never guess. It's just like an electron, but it's positive. So hang around the positron. Don't hang around the not the negatron. Don't hang around the electron. We're going to leave that last column blank. We are going to come back to that. We are going to come back to that. So leave that blank for now. What info can we get from a periodic table? It's a pretty powerful tool. All info, not just in nuclear physics. Yep.
Oh, you can get subatomic particle numbers.
What else? Do we really know how many electrons we get when we look at our... sorry, so I just want to put a line through that. We sort of do, we sort of don't. But we definitely know how many protons and neutrons we get, correct? We definitively know that. What else do we get?
Molar mass.
Oh, very good. What else?
Vanadium shell configuration.
I'm just going to put electron shells, but yep. What else? I'm just going to put properties because you're correct.
Charge.
Yeah, I'm going to put that in electron shells and properties, but yes, you're correct.
The symbols for that.
Yep, so symbols, the names. Cool. We'll leave it there. We don't need to go any further. There's plenty more. The periodic table is a great tool. Now, some of these things are dealing with chemical reactions and some of these things are dealing with nuclear reactions. What are nuclear reactions all about? Reactions in the nucleus. So which of these matter to our nucleus? Does the electron shells, does that matter? So that's not important. Do the properties of the material matter? Not the chemical properties. The nucleus properties, yes. Does a symbol and name really matter? We don't really, I mean, it sort of does, but sort of doesn't. We need to be able to use the periodic table. Does the molar mass matter?
Yep. I mean, wait, no.
Atomic mass does, but molar mass does not. So realistically, the information that we need to get out of our periodic table in nuclear physics is number of protons and neutrons and the atomic mass, which tells us the expected number, whether we have an isotope or not. Contrast, fusion and fission. I want you to give an example of those while